Welcome back to Logic, Language and Information. In this lesson, we will finally discover how PROLOG goes about answering queries. From Lesson 6.2, we know how to write program clauses and logic programs in PROLOG notation and how to ask PROLOG whether or not a goal is a logical consequence of a logic program. In this lesson, we'll get inside PROLOG to find out why it gives the answers it does. Let P be a logic program and G a goal. The proof rule within PROLOG is going to allow us to derive a new goal, G prime, from the given goal G by consulting clauses A and P. Repeated applications of the rule produce a chain or sequence of goals. Technically, the rule implemented in PROLOG is called SLD resolution, standing for Selective Linear Definite Clause Resolution. And remembering that definite clause is an alternative name for program clause. A linear tree diagram can be used to depict a sequence of rule applications producing a sequence of goals, with clauses A from the logic program P appearing as side inputs to the linear sequence of goals. Allowed among the goals is the special case of the empty goal, denoted by the square symbol, and thought of as the empty list of atoms, whose meaning is contradiction or always false. PROLOG implements a refutation procedure, like proof trees. Suppose all clauses in the program P are true, but the initial goal G has at least one atom false. Then PROLOG starts from G and tries to derive the empty goal, square. So, what is this resolution rule? Well, given a goal G whose first atom is Q and perhaps has some other atoms following, PROLOG will look for a program clause A and P whose head is Q. If A is a conditional rule, Q if P1, P2 up to Pm, then the new goal G prime is obtained by replacing Q with the body atoms P1, P2 up to Pm from A. The new goal G prime is called the resolvent of G with clause A, with the new first atom P1. Under the refutation interpretation, we are supposing that G is false and all the clauses in P are true. If it is atom Q in G that is false, then under the principle of modus tollens, or denying the consequent, as in my t-shirt, we can infer that one of the P1 or P2 or any of them up to Pm must also be false. So we get the new goal, G prime, as described. The resolution rule works even more simply in the case of fact clauses in logic programs. Again, we start with a goal G whose first atom is Q and perhaps has some other atoms following. And again, PROLOG will look for a program clause A and P whose head is Q. If A is simply the fact Q, then the new goal G prime is obtained by simply deleting Q from G. Again, the new goal G prime is called the resolvent of G with clause A. And now the first atom is R1, if there is one. In the case that G is just Q alone and there are no R's, then G prime is the empty goal, square. So PROLOG is trying to find a resolution refutation sequence, starting with the given goal G and leading to the empty goal. Now suppose we have loaded into PROLOG a logic program P and we have a goal G, where all the atoms in the goal must occur as heads of clauses in P, so there will be no error messages for that reason. Then PROLOG will answer true to the query if and only if PROLOG finds a sequence of goals starting with G, with successive goals, the resolvent of the previous goal with a program clause in P, and with the last goal in the sequence empty. This is a resolution refutation sequence. Let's go back to our sample weather program from lesson 6.2. The query of the goal high fire danger is answered by PROLOG with true. What is the resolution refutation sequence used to answer this query? Starting with the goal high fire danger, PROLOG looks for all the program clauses with high fire danger as its head. There is only one of them. The first resolution step then produces the goal G1, the list of 3 atoms, windy, dry, hot 35. In goal G1, the first atom is windy, so it is processed first. PROLOG looks for all the program clauses with windy as head. There are 2 of them, so PROLOG starts with the first one in program order, but also marks that there is a choice point, meaning that there is another clause to try with windy as head. The first one is windy if Melbourne, so the resolvent goal G2 will be Melbourne, dry and hot 35. The first atom in G2 is Melbourne, so PROLOG looks for all the program clauses with Melbourne as its head. There is only one of them, Melbourne if false. The resolvent goal G3 then has the constant false as its first entry. This is not allowed and signals a dead end on this line of reasoning. PROLOG then backtracks to the goal G1 at the last choice point and proceeds from there with the second program clause with windy as its head, namely windy if Yakandanda. Australians like abbreviations, we're going to use Yakka for short. Proceeding from here, the new goal G2 becomes Yakka, dry, hot 35. The fact Yakka is then in the program then gives a resolution to the shorter goal G3 consisting of dry, hot 35. Then PROLOG looks for all the program clauses with dry as its head. There is only one of them, dry if Yakka. 2 steps of resolution, then get down to goal G5, the single atom, hot 35. PROLOG then looks for all the program clauses with hot 35 as its head. There is only one, hot 35 if Northern Victoria. 3 steps of resolution, then gets to goal G8, the empty goal. So success. The original goal, high fire danger, is a logical consequence of the logic program. After excising the dead-ending backtracking detour, we can see the cleaned up resolution refutation sequence for this successful logical consequence query. Now, the next possibility, what if PROLOG answers false? Under the reasonable assumptions on P and G, PROLOG will answer false to a query if and only if a systematic depth-first search does not produce a resolution refutation sequence, ending with the empty clause, where the search is through the tree of all possible resolution sequences starting with G with input from clauses as ordered in P. There is branching in this tree whenever there are 2 or more program clauses whose head is the active goal atom. So the search point marks a choice point. The refutation approach in the proof tree method we saw in the core part of the course has the added bonus that a no answer brings with it a valuation which makes premises true and conclusion false. This is not the case for the resolution method for PROLOG here. A false or no answer here does not bring with it the useful semantic information as provided by a proof tree with an open branch. So we've now covered the case of a true answer and a false answer. What about the depressing third option that PROLOG is unable to give an answer? Again, we start with reasonable assumptions on P and G to eliminate needless error responses. And in response to the query, PROLOG can sometimes crash and fail to answer. For example, this will be the case if program P contains an implication loop, such as this one, P if Q, Q if S, and S if P. And this loop can be accessed from the initial goal via resolution steps. For example, consider the little program loop-001.pl. As shown, we have P if Q, Q if P, and then the fact Q. It should be clear that the atom P is a logical consequence of this program, because together the program clauses assert P if and only if Q, these two together, plus Q. Now, let's ask PROLOG the query for goal the atom P. We get a stack overflow error as PROLOG chases its tail around the implication loop P if Q and Q if P, with the resolution goal alternating between being atom P and atom Q. In particular, the third clause asserting fact Q is never reached. This number, 3,900,000 and something thousand, is positioned in the stack, and you can count your way down. We are left with an incompleteness problem, that atom P really is a logical consequence of this program, but PROLOG cannot produce the answer true. We have so far given a quick argument as to why resolution is sound. If we rewrite the relevant formulas as disjunctions in clausal form, it's going to be easier to see what's going on. First, program clauses, including facts, the case when m equals 0, these are logically equivalent to a disjunction Q or not P1 or not P2 or up to not PM. In the case of facts, when m equals 0, this just reduces to the atom Q on its own. Now remember, a goal is just a list of atoms, and the goal formula is the conjunction of those atoms. But since we are using a refutation procedure, we are supposing that B is false. So the formula of interest is the negation of B, which comes out as logically equivalent to the disjunction, not R1 or not R2 or up to not RK. Now, a little terminology. A literal is an atomic formula or the negation of an atomic formula, and a clause is any disjunction of literals. So we've seen program clauses are clauses and negated goals are clauses. Expressed in clausal form, program clauses include exactly one positive literal, their head, and the rest, if there are any, are negative. So clausal form is sometimes written as just a set of the literals. For the goal, we look at the clausal form of the negated goal, which will have 0 positive literals because all of them are negative. A logic formula is called a Horn clause exactly when it is logically equivalent to a clause with at most one positive literal. So this combines program clauses and negated goal clauses into one class. Resolution methods were first developed for the Horn clause fragment of logic and then specialised in the implementation of PROLOG. The refutation approach puts together a logic program with the negated goal and tries to derive a contradiction. This means showing that this combined set is unsatisfiable. Expressed disjunctively in clausal form, the negated goal clause expresses that at least one of its negated atoms is true. Resolution on the atom Q within a conditional rule simply cancels out the not Q with the Q at the head of the program clause. So the resolvent is the union or merge of the two clauses after cancelling. Resolution of the goal on atom Q with the program clause fact Q likewise cancels out not Q with Q in the program clause. So the resolvent is just the smaller negated goal clause without the not Q. Seen this way, resolution is just cancelling out negation pairs. Soundness requires that if a negated goal clause for G is satisfiable, then the negated goal clause for a resolvent G' must also be satisfiable, with G' the resolvent of G with any program clause. We summarise the soundness or correctness of propositional prologue. Given a logic program P and goal G, if prologue answers true to the query of G, then G really is a logical consequence of P. If prologue answers false to the query of G, then G is not a logical consequence of P. But there is incompleteness. Prologue can crash and fail to answer when G is a logical consequence of P, as we saw in the loop example. This brings us to the end of this lesson explaining the workings of prologue. The last brief lesson in this series, lesson 6.5, will raise the topic of negation in prologue.